All right, let's talk about AI, video games, and the singularity. We're going to be talking about complexity, optimization, and what it is that AI is actually up to without a tremendous amount of technical details. So let's try and get into this. So first of all, AI is a form of, in its most basic incarnation, a form of optimization. So optimization means finding new solutions to something. So you have some kind of problem. There exist optimal and suboptimal solutions for whatever it might happen to be, or a, optimal or suboptimal point on the function. And you find a routine, some kind of algorithm that gives you that optimal solution or set of solutions. Now, this can be as simple as Newton's method in trying to find, where is the minimum for a function, or it can be, gratuitously much more complicated. And that's where video games come into the picture, is trying to imagine different layers of complexity. So that's foreshadowing a bit. Now, one of the most basic forms of this, and I think I'm somewhat biased based upon the, little bit of education that I had in electrical engineering. One of the most basic machines that we have today that everyone deals with is a thermostat. And the idea that a thermostat performs a kind of optimization and performs a kind of intelligent function is interesting, but at the same time, it's also obviously electrically a very, very simple system. So it's an optimization routine. It's not just pure mathematics, but at the same time, it's something that everybody has practical experience with, and it's obviously not a human level intelligence. So that's one end of the spectrum. Now you've got that. But then on the other side, you have things that start to require human levels of innovation and creativity and problem solving. And trying to pin down exactly where that point is crossed can be very difficult, because it's not purely a matter of complexity, and it's certainly not a matter of a mass of information. So you might be inclined to say, okay, well, a thermostat only exists along one dimension. Let's take a look at several dimensions, or maybe in dimensions. Does that actually help? I mean, of course not, right? I mean, Newton's method in dimensions, we're still talking about function minimization. It's still something that doesn't smack of intelligence. And so no matter how many dimensions your thermostat is working in, let's say you have temperature and humidity and you have, other, maybe it has to do it quickly or whatever it might happen to be. That's not going to get you to intelligence. Like, it's fairly obvious that adding complexity there is not going to get you to something that recognizably is intelligent behavior. So what happens? Where does that have to happen? Okay, well, you might be inclined to say, well, in the realm of mathematics, let's look at theorem proving. Well, theorem proving, obviously, there are certain forms of that are discrete, and I've got a handful of rules, like maybe I'm working with Euclidean geometry, and I've got a handful of rules that I can apply. Here's my starting point and what I know so far, and I'm going to kind of mash up each of those combinations until I get something that's actually workable and gets me from point A to point B in doing the derivation. Well, okay, that's one way of doing it. You can obviously do that in a brute force, tree search or something of the kind to try and do geometry problems. And indeed, if you don't know anything about how to proceed in a geometry derivation, a proof, then that may be what you do. You just try a bunch of stuff, you see what works, you keep the stuff that works, and you continue to work, improve upon that until you get to a solution. And then maybe if you do it enough, then you say, okay, well, maybe a shorter solution is better. That's still brute force, right? Even a tree search of, Euclidean geometry proofs, this is still not really intelligence. It's fairly obviously not the kind of thing that we would recognize as intelligence, even though it is potentially a very complex and maybe even useful form of optimization. So what's the difference there between that kind of theorem proving and one that's actually interesting? So there was an example recently with alpha geometry, and this is out of Google DeepMind, where alpha geometry was a system that was competing at the International Olympiad version of or level of geometry problems, proofs. And it was able to compete well at that level because it did something different. It wasn't just a brute force tree search. It wasn't just in the realm of formal logic. It was also doing something with an LLM in the loop. In other words, a large language model was used to try to accomplish some of the more creative aspects of geometry problem solving. Because the idea is something like this. You have a, set of things that you're given in the beginning. And I think everybody kind of pictures like an SAT question or, high school geometry or something of the kind, unless you happen to be a math major. And then you probably have a lot of other examples. I was a math major. So anyway. But so you have your kind of going in stuff that you know. But that may not be everything that you need to actually accomplish the proof. You may have to infer information based upon what it is that you already have. Like, I may have the different sides of a triangle. I may have the different angles and that sort of thing. But it might actually help to drop an altitude. Like it might help to actually draw a new line, create a new quantity, and then start working with that new quantity and the new triangles and other things that it creates. Oftentimes, that's what we have to do to be able to get from point A to point B and actually solving one of these problems. And in doing that, this is the miracle step. So this is the portion that requires some kind of intuition. It requires some kind of seeing with the problem and saying, I think that's necessary. If I only had this kind of information, then I might be able to actually finish the proof. How might I get that information? Or you might have an intuitive grasp that, okay, look, this is the sort of problem that if I had these other couple of quantities, like I draw a tangent line or I draw an altitude or whatever it might happen to be, then that's suddenly going to make the problem tractable. And that kind of intuition is not a brute force tree search. That's something that looks more like associative thinking. It looks more like the kind of human-like thinking that goes on with people. And so that was very interesting. And we'll have occasion to come back to that example because it's instructive in the way that we're trying to get to all of the different human levels of capability with AI. Now, that being said, the difficulty here, I think, is trying to determine where that line is. How do we draw the line between just a, brute force decision tree type organization of things and how do I, suddenly I have something that looks more human. It behaves in a more human way. There are people, for instance, there was one blog post that was written about this is kind of following along with the so-called Sparks of AGI paper that came out of Microsoft in 2023. And that paper gave us some kind of indications that, well, even if we can't show it entirely, even if we can't fully argue for it, it seems like there's something going on there. It seems like there are some sparks of intelligence. It seems like there, intuitively we can kind of see that there's something extra happening. That's very interesting. And the blog post that I had in mind was by someone who wrote about ghosts that were inside. So ghosts in Claude or ChatGPT or whatever it might happen to be. And that follows along the lines of what we got from Alan Turing in 1950 with the Turing test. So the Turing test is one that is beautiful for a variety of reasons. And is it the final word? No, I'm sure it's not the final word, but that's not the point, right? It's actually really clever because it trades on human intuition. The Turing test tells us that if you have a person who is interfacing with an AI just purely on a text basis, and so they're sending messages back and forth. I mean, these are the chatbots, right? We've got this now. They're sending messages back and forth. If that person can't tell that they're, not talking to another person, if they can't tell that they're talking to an AI, then it has reached a, level of intelligence. It is intelligent. Well, so obviously, I mean, that's not the extent of what it means to be human and all of these other questions. But the point is, it works on human intuition. It works on the ability of one person to intuitively recognize, to sympathetically identify with what's going on in the other person's mind. And this is also called model of mind, where we try and imagine what another person is thinking. And we can intuitively grasp what another person is thinking in contact with that person for an extended period of time. And it doesn't have to be very long. I mean, if you have someone, my favorite example of this, because I've written on this. So in my book that came out in 2023, and then also building on an article in 2018, I described the idea of connoisseurship. And connoisseurship is the ability of one expert to recognize another expert, to recognize someone who is about at the same level of expertise or less. If they're too far above you, then it doesn't work. But nevertheless, we have an intuitive grasp of this sort of thing. And so I had experience of this when I was asked to go in as a visitor to a class that was learning, clinical psychological techniques. And so I was asked to do a role play and said, okay, pretend to be a pianist who has stage fright. And I said, oh, okay, well, this will be fun. I'll pretend that I play with the Atlanta Symphony Orchestra and that I was having trouble with, nerves before the performance. And so I did this. And there were people who came up after me, after the class and asked, did you really play with the symphony? Did you actually do that? Are you a pianist? And I said, well, I play piano, but it's a pleasant fiction. Like, no, I never played with the symphony. I'm not that good. But The point is, if they didn't play piano, if they are not at the concert level, they couldn't tell necessarily, because the difference between a charlatan and someone who has actually got that kind of magical level of expertise, it's very difficult to tell if you don't yourself possess the expertise. Now, when it comes to the Turing test, what this means is that we all possess, the qualia. We all possess the what it's like to be human. And so we can attest to what that's like, and we can recognize it in other things. And arguably, that's the kind of thing that we do with not only other humans in different levels, right? With children who have matured somewhat, with experts in different ways, with those who are, very bright, et cetera, et cetera. And so there are all kinds of different flavors of this, but even more than that, even with animals. And I think this is one of the arguments that really doesn't get mentioned very much, maybe enough, with dogs and cats. And I heard it recently with dolphins, where someone had encountered a dolphin and was interacting with it and said that it was actually uncanny to look the animal in the eyes because there was some light on, like there was something going on. And it was that intuitive level of there is something happening. There is intelligence there. I can't put my finger on it. It's not human, but there's something there. And that's the same kind of thing I think that we get with, dogs and cats and pets and whatnot. And people now, of course, have all kinds of different pets. And so you get a really wide variety of this, from those that barely know that you're there to those that are, highly interactive and ostensibly sharing in a lot of very human emotions and maybe even thought patterns, which is why it's strange to us when you have a dog that you interact with as though it were a member of your family, but then it doesn't seem to understand the concept of a leash. It doesn't seem to realize that it's connected to something and will, do some almost, hilariously stupid things sometimes because it doesn't understand some things that to us are very, very obvious. And so that's the kind of intuition that the Turing test is built on. That's what they're trying to get to by this, is to say, okay, let's take that estimate of expertise and use it to assess something with artificial intelligence. Now, that may seem, okay, well, a little, woo-woo or kind of nebulous, and it's certainly not the sort of thing that's going to be objective and easily nailed down. But at the same time, it has a long history and it has significant precedent in education. Because not only is that how the medieval universities used to do it in terms of disputations and the way that they assessed expertise of others by talking with them, that's an excellent way of doing it. But it's also still the vestige that we have of that even in modern day education, which is much more mass produced. Even there, we still do it at the doctoral level. And so doctoral dissertation defenses are still, one-on-one or one versus many sort of conversations and interactions. And the idea there is very simple. Can the experts recognize you as another expert, or do you still have further to go? And so we're using the Turing test essentially for academic PhDs. We're using the Turing test to try and determine whether or not somebody should be let into the group if they have become an expert in that way. Okay. So now, what's salient about history with this? And basically since 1950, I mentioned that date not out of coincidence. It is indeed a significant milestone. And this is also the beginning of when we start to see, real work done on creating computers. And so this is when the snowball starts to really build in terms of technological capability, analog first and digital. And then you had all these, ridiculous advances in the last, 75 years or so. And it really has taken off. But even at that time, even in the 1950s, we started hearing about evolutionarily inspired algorithms and evolutionary methods to try and grow an intelligence, to try and grow an optimization solution. And you might think, especially if you're familiar with evolutionary computation. So evolutionary computation is the field that studies, the subfield in mathematics, that studies genetic algorithms and genetic programming. And genetic algorithms and genetic programming both, but GAs are more common, where you essentially have a vector of numbers. It's just or a tensor, if you like, a string of numbers. And it's a DNA strand. And you can treat it like a DNA strand, and you can splice and recombine and mate and have tournaments and all of that. I mean, it's all the usual stuff in terms of survival and mating and mutation and crossover. And it borrows a lot from biology there to try and find optimizations in areas that otherwise the space of possibilities is just simply too large. The search space of all the different possible animals that you can make, all the different possible ways in which you can tune all of these different knobs. that search space would be way too large to optimize using any kind of brute force method. Newton's method is almost certainly going to miss it, and a lot of the other methods are going to miss it in terms of probably not finding the global optimal solution. But genetic methods, so evolutionarily inspired methods, do very well with this. Well, they do very well with this, building from what it is that we already see in nature. And that is part of a class of algorithms and approaches that attempt to grow an intelligence rather than designing an intelligence. And that difference could not be starker or more important. So that's something that, especially now, that we need to pay attention to, because this difference between what is designed and programmed in and what is grown is profound, because what is designed and programmed in tends to be limited to and has a kind of ceiling of the person who's doing the programming. And so your program that you're writing, no matter how sophisticated and magical it is, it's not going to be more sophisticated than you are. Your understanding of that situation is kind of a ceiling for the program. And so you're trying to design pieces of that program and stack up blocks, but you can't stack higher than the ceiling. And so a grown intelligence, however, is simply a, kind of a mixture of ingredients. And you put all this stuff together, you put it in the right environment with the right constraints and rewards and whatnot, and then you hit go. And most of the time it doesn't work, and it miscarries and has all kinds of terrible things that happen. Maybe it finds a, degenerate solution, or it just kind of flounders around and doesn't do much of anything because you've got the wrong reward or whatever it might happen to be. There are lots of ways of getting it wrong. But by the way, evolution discovered a lot of ways of getting it wrong too, right? I mean, in some of these cases, especially in very early stages of evolution, we're talking about hundreds of millions, billion years between, major changes. And so it takes a lot of searching sometimes to find and modify all of these things to get something that's worthwhile. But nevertheless, growing something means that the complexity constraints of the original system are not the ceiling of growth. It means that you can continue to go beyond that, and that the systems can grow in complexity and grow in sophistication and intelligence beyond any of the original parameters. So the original parameters themselves are not constraints in terms of an upper bound of performance. Well, obviously that's really important, right? Designed algorithms, yeah, okay, that only gets us so far, and Tesla found this out the hard way in trying to design self-driving cars in this way, so that they had hundreds of thousands of lines of code that were in, full self-driving. And it worked. Like they were able to finally get there, and it took forever and a lot of money and a lot of, oops to try and get there, but it got there, and it was a little clunky, like it wasn't totally human. Well, they replaced this recently with, I think this is 2023, maybe 2022, with a full neural net architecture for it. So they trained instead something totally different. In other words, they grew an intelligence to try and do this. And it was much smoother. And it is much smoother. Now, it has its own issues and kinks that they're working out and whatnot. And so it's not perfect, but at the same time, it's obviously doing things in a more organic feeling fashion. And that's significant. And the fact that it doesn't have a ceiling because of that, that is also very interesting. It only has ceilings based upon its rewards, its constraints, its environment. And you see the same thing with animals, right? Some animals will evolve to a certain point and then they just kind of stop and stay the same for a really long time, turtles and alligators, So it's not necessary for them to do much more. Maybe they have reached a kind of optimal within their, particular niche. And, computer programs and optimal solutions there do the same kind of thing. And so for us, it's a matter of trying to find out, how do you set up the parameters of the game? How do you set up the parameters of what it is that you are designing in terms of the optimization primordial soup, so that it will eventually produce something that will be very valuable and will grow beyond and to the point where you need it to grow. So anyway, that's I think very interesting, and it gives us reason for thinking that the kind of cheap arguments that you hear against AI sometimes, it's like, oh, it's just programmed, it's just it's whatever the programmers wanted it to do. Well, no, the programmers don't know how it works, and in many cases, we really and truly don't know what's going on, to the point where we don't know what they know. We don't know what the large language models actually know. We don't know how clever they are. We are having trouble trying to figure out just how smart they are and even what they are based upon the ingoing architecture. something magical was unlocked with the Attention is All You Need paper and the creation of Transformers, the Transformer architecture in 2017 out of Google, but everyone there has since gone on and left, but nevertheless. So something was unlocked there with the attentional mechanism that allowed for capturing complexity for the purpose especially of prediction in a way that was not previously possible. But we'll return to that. So let's talk a little bit about the history of where AI has come from in terms of its capabilities and how it is that things have changed over time in ramping up in complexity, and how it is that this may change the way that we interact with it. So the way that I interact with my thermostat is a lot different than my interaction with my dog, and all of the shades of gray in between. The way that we interact with our cars. I'm not likely to anthropomorphize my thermostat as much, but I might anthropomorphize my car and, talk about, well, she's been doing well today and likes to do this and has a certain personality because cars have, eccentricities of their own. And complex systems have eccentricities of their own. It's like they have individual personalities based upon all of the combined, faults and capabilities. And at a certain point, then this crosses over and becomes something that's apparently more organic. And the question is, what is that secret sauce? What is the missing ingredient there? How should we characterize and understand that complexity that allows us to go from an apparently inorganic intelligence to an organic intelligence? So we can see some of this with the story of the history of AI. And what I want to highlight is the history of AI specifically with playing games. And so one of the first games that people tried to get AI to play was chess. Now, chess is popular, but it's also simple. Chess is a very small matrix, really. I mean, if you're talking about an image, especially if you got like a 4K display or something, a 16 by 16 image is going to be so tiny you wouldn't be able to see it. And so we're not talking about a tremendous number of possibilities. We're talking about something that's actually quite small. And so you have just a few pieces, you have just a few spots on the board, and out of that emerges a, fantastic landscape of possibilities in terms of all of the different moves and strategies and what you can infer about what your opponent is probably thinking or planning several moves in advance and that sort of thing. And so even out of this very simple setup, even out of a very simple set of equations, you get disproportionately complex behavior. Does that sound familiar? I mean, we see this with fractals. We see this with emergent behavior of a variety of flavors. And so in Conway's Game of Life, let's say, where you have a Minesweeper used to be that. Nobody really plays Minesweeper as much anymore that I know of, but nevertheless, so you've basically got a pixel grid, a two-dimensional matrix of, white and black squares. And you have certain starting conditions. You paint in whatever the starting conditions based upon ones and zeros, so white or black squares. And then you have certain rules that govern, okay, well, if this white square is next to a black one and a white one, then turn it black. Or if, you have just a few simple rules, and out of those few simple rules, depending upon what you do, you get, almost magically complex behavior and emergent behavior. And it might seem like, okay, you've got some, lights and whatnot flashing on screen. But no, it is actually emergently complex in the sense that it actually models physical systems of various kinds. For instance, the growth of bacteria colonies. That kind of thing, and the way that things spread and then have, certain regions of localization and stability. And then all of a sudden you'll have something that happens and it disrupts the system. And there's all kinds of fantastically complex and interesting things that happen with that, even though the starting conditions were very simple. That's a phenomenon known as complexification, where you have a radically different in kind, arguably complex output based upon a simpler input. And of course, we're very interested in those kinds of systems for obvious reasons, because in the biological world, there's the question, okay, well, how does life emerge from non-life? How do we get complexity from non-complexity? How is it possible for something to give birth to a more complex organism? And that's not obvious. And this is something in philosophical history, and we'll have occasion to talk about this more. In philosophical history, this was in violation of one of the principles going all the way back to the ancient Greeks, which is that like tries to create like. Things try to recreate themselves. And so things try to create and give birth to what is most like themselves. And that may sound awkward and strange just because we're not familiar with it, but biology. Acorns. Oak trees try to create oak trees, and they try to create oak trees by producing acorns. Acorns have the latent potential to become an oak tree. Simple. Same thing with human children. And you might say that it even goes down to the individual level, because at an individual level, individuals try to create what is most like themselves as individuals. And you can see this in children, that the children actually resemble their parents more than they resemble the population in general. That kind of thing, that kind of data that would have been open to anyone even 2,500 years ago, that led to thinking along those lines, that like likes to create like. And so that's kind of the forerunner of what we're getting now. And one of the possibilities then in talking about especially ancient philosophy is that they were not aware of emergent phenomena. They were not aware of things in the biological world, in the mathematical world, and otherwise, that a simple set of circumstances and starting conditions resulted in something that was out of proportion, disproportionately more complex. That opens the door for the creation of complexity, not just entropy kind of descending into chaos, but actually the creation of complexity, which means that you no longer need a divine origin for life. You no longer need a divine origin for any kind of complexity, and things snowball and become problematic for ways that we'll have occasion to go into. So anyway, there's that. So we started with chess, very simple game. And IBM had a program called Deep Blue back in the 1990s. And this is 1996 and 1997 when this was, televised, or it was made popular. And Deep Blue played Garry Kasparov, who was the reigning champion, chess fame. And 1996, it lost. I mean, it didn't lose everything, but it lost. It lost the match. In 1997, it won. And so Deep Blue beat, for the first time, a computer program beat a grandmaster, and in this case, like one of the world's greatest grandmasters in chess. And so the thought was, okay, well, does that make chess like a non-issue? Are people even going to play chess anymore because you can't be as good as the computer? And that was what some people were saying is, oh, this is the end of chess. Well, it wasn't the end of chess, and we know that now. And people still like playing the game because, as it turns out, there are other reasons for playing, aside from just being the best, which I think is intuitively obvious to your average person. But maybe if you're thinking too hard about the individual details, then you might miss that. But nevertheless, so we've moved up from there, and it's like, okay, chess, that's one type of game, and that's a relatively simple and very discrete and rule-oriented game. In other words, it is not a continuous game. It's not where it can move like marbles. Let's say if you're playing marbles, that is a continuous game. It's one where you don't have a discrete number of possibilities. You have a continuous valued field of possibilities where the marbles can exist in different places and then interact based upon physics and so on and so on. So it's actually a substantially complicated game. Well, okay, so one of the next natural places to look was something like Super Mario Brothers. And so Super Mario Brothers, the side-scrolling, like you have two buttons, and then you have the directional pad. Well, the directional pad is not a continuous function either. That only has up, down, left, right. And so you have up, down, left, right, A, B, and then you got the other two buttons in the middle that aren't really used in the game. So you've really only got 6 possibilities for actually controlling Mario. And you've got this over time. So, all right, there's the time component. You have to be aware of what's going on in your environment, which, by the way, is still discrete, in the sense that the way that sprite-based games were written is that you had little sprites. They were these little boxes, these little images, and the sprites would be painted in different places. And so Mario actually is set up like a grid. It may not look that way. It's designed, obviously, not to totally look that way, but it is. And so that makes it a little bit easier. So it's not, completely and utterly fantastically more complicated than chess, but at the same time, it is more complicated. And so what you end up at the end is an optimal string of button presses. Well, okay. Does it understand what it's doing? Well, Deep Blue didn't understand what it was doing. I mean, it was basically it was like a 16 depth tree search or something where you had, looking 16 moves in the future, all of the different possible moves. And so Deep Blue considered absolutely everything, like millions of possibilities, more than any human would ever reasonably consider. And far more than Garry was considering. So Garry Kasparov, it was likely that he was only considering a few moves at any given time, because an expert doesn't become an expert by considering millions of moves at the same time. They become an expert by honing in exactly what it is that they consider, so that they only consider a few possibilities. But all of those possibilities that Garry was considering were probably really excellent possibilities. They were probably all really good strategies and really good moves. But he tried to select those that were better for whatever the circumstances might have dictated. So Deep Blue didn't think like a human. That was clear. And the, solutions that we have, neural nets that are trained to actually play Super Mario Brothers, it's not really thinking like a human either. Not quite. Like there's some sophistication, there's some interest there. There's something more going on, but it's hard to put our finger on exactly what it is. But it still seems like it might be a stretch to say that it understands the game of Super Mario Brothers, especially insofar as that doesn't transfer to other places. And transfer learning is one of the keys in artificial intelligence. So this is one of the holy grail of artificial intelligence, to be able to train a system in one place and then have it take that skill and transfer it in vivo to another environment. That turns out to be a pretty hard problem. And so, but humans do this pretty well. We do it well, and we adapt our knowledge, and our knowledge is all kind of promiscuously interconnected in that way. And so it's been a challenge to try and get computer systems to do this. Well, a few years later, with Go, the game of Go, and AlphaGo, again out of Google DeepMind, in the 2015 to 2017 timeframe, and then with AlphaZero 2 years after that, and now MuZero, AlphaGo was able to defeat the grandmasters, the best, 9 Dan level of Go players. And Lee Sedol famously was one of them and said, okay, forget this. I've been defeated. Like, I can't win against this thing. I give up. Like, I'm done. I'm not playing anymore. And that was more along the lines of what people were afraid of, that as the computers become better than us, we wouldn't even want to play the games anymore. But what was interesting about that is that Go, although it is a grid, it is something that is, kind of chess-like, but it's also deeply psychological, and it is more involved. It is more complex than what we get with chess. And so there was the thought, after people saw success with chess, it's like, okay, you've done chess, but you're not going to be able to do these other games. There are other games you're not going to be able to, actually have success with. But they did, right? They were able to get success with this. And then beyond that, it's like, okay, well, what comes after Go? Well, StarCraft is one of the examples. And StarCraft is an even more continuously defined open-ended game. And that's the sort of thing that, okay, if you can train a artificial intelligence to do that, then that requires even more. Okay, well, moving beyond that, one of the ESPN8 games with AlphaDog a couple of years ago. So AlphaDog was having fighter aircraft battle each other. So in this case, an AI versus a human in a cockpit simulator. And that's a deeply psychological game. It's one where you have to try and outfox your opponent. And you have to get in their head and try and anticipate what they're going to do and outsmart them. And so it's not just a mathematical game. It's really a psychological game. And the computers now are able to win at that. Okay, so now we have continuous value games. We have psychological games. What's next? Well, what about open world games? And now you see computers that are succeeding at Minecraft. So Microsoft, and this is in 2023 and 2024, demonstrated the ability to be able to, become accustomed to an environment, collect resources, plan things out, actually go about making, and I'm not a Minecraft player, what is it, the diamond sword or diamond pickaxe? And, goes, the point is, you're able to work in a completely plastic environment, one that is subject to any kind of modification that you might want to make in terms of, destroying things, creating things, trying to navigate all of the different possibilities in terms of terrain. And it is continuous valued in the way that you move around, and open-ended in the sense that you can do anything at any time. And so being able to do that, well, what's left? What kind of game is left? If you think about all of the different video games that people play, you have a certain kind of input in terms of, the different controllers. So, just think about the evolution of controllers over time, where you have, like I said, the D-pad on the original Nintendo back in the 80s, where it's discrete. You only have up, down, left, right, A, B. But then we started seeing analog control sticks. And then we started seeing lots of buttons. And so you have analog controls, you have lots of buttons. The amount of complexity going into the input has increased to the point where, okay, what is the edge in terms of what a human can keep up with? Like, how many keys, how many buttons can they interact with successfully? And as it turns out, it's pretty wildly complicated. People can get used to using some very sophisticated tools. And the fact that you have the, Xbox and PlayStation remotes that have so many buttons and so many different controls and possibilities, the analog sticks and otherwise, that's a testament to just how much complexity humans can handle and are willing to learn for the sake of these games. But the games are a proxy for complexity in all kinds of things for which we might want to define algorithms and design optimal flows to solve problems. So this could go as easily to medicine, it could go as easily to war or to politics or to anything. And the question is, with a game like Minecraft, if you can do that, if you can do long-term planning, resource gathering, creation of structures and modifying your environment and, interacting obviously with whatever input complexity that you might have in all different modalities, where before it was just getting non-visual information. Well, now they're getting visual information. They're getting visual audio information. They're getting the discrete inputs, and they may even keep up with their own, statistics and whatnot in terms of what would be useful for them to think with during the game. And this is all done now using multimodal models that are natively multimodal, not just slapped together, not things where you've got one that does vision, one that does audio, one that does text. Now the whole thing is coming together. OpenAI demonstrated a model with GPT-4o with this in May of 2024. And then shortly after that, a month later, Meta comes out in June of 2024 with a version of Llama that does this, where it is natively multimodal and is a medium-sized model. In other words, along the range of like 13 billion parameters or so. And so these are models that can actually run on consumer-grade hardware. So you could run it on your, consumer-grade graphics card. Not necessarily your home computer, unless you have one that actually has enough RAM and capability to do it. But nevertheless, so it's kind of big for a consumer card, but it's not huge. And this is happening, and this is coming together. And so being able to play these games, being able to play ostensibly any video game, is that true? This is worth thinking about. Like, take a second and think about this one. Are there any video games left now? If you can do chess, Go, Super Mario, StarCraft, Minecraft, what's left? What other kinds of complexity in video games is not accounted for by having it play games like that? So take some time and think about that one. And I'd be very interested to hear any examples that you might have. I've been involved in that space for a long time. I'm not a huge video game person, but I've been involved in it and interested in it for a long time for all different reasons. It's fun. And it also has, aspects of especially computer graphics. I was always very much into computer graphics and digital painting and that kind of thing. But then also with optimization, the mathematics, and now the intelligence side of it, how it is that the computers play the games. And so very interested to see now, okay, now that we've done Minecraft, what else can we do? How much further can this go? And that game playing technology, by the way, is precisely the sort of thing, because if you wonder whether or not this is practical, so DeepMind is a great example of this at Google, where they have the shop that's, learning to play Go and learning to play StarCraft and Super Mario. And that might seem kind of, okay, whatever. But MuZero, the follow-on to AlphaGo in 2019, MuZero was able to take that and transfer that capability to play Atari games, which means that it has learned something about game playing. It has learned something about game playing in general, not just playing that one game, not just an optimal solution like your thermostat has for trying to regulate temperature in your house, but actually it has learned something substantial that it seems like might even be an analogy for human understanding with respect to gameplay that transfers to another environment. Now, that would be significant if that's the case. Out of that same shop comes AlphaFold, and comes some of their other products that are like that. And they're now up in different iterations, in several iterations with AlphaFold, and being able to do protein folding, which in the biology world, I mean, if you kind of have to take the biologist's word for it that, hey, this is really significant, because your average person has no idea what protein folding is. But suffice to say that trying to understand, especially chemical interactions in the body, in the way that proteins are formed and interact with chemicals and do different things, a lot of it's based on shape. And so that folding, how it is that those particular molecules are going to form, that matters a lot. It's not everything. We don't get designer drugs immediately, right? We're not going to have individualized medicine where you design a drug that is specifically for your chemistry and it's going to work perfectly for you with no side effects. That's the goal, right? Is to be able to do very targeted interventions of things for your particular body chemistry. That's the goal. And that's the kind of thing that could eventually be enabled by additional advances in this. And it started by learning to play Super Mario Brothers, right? And it started by learning to play Go and StarCraft and the others. And so games are serious business in this way. And they're serious business in AI because there's an argument that games are a way of understanding how it is that we go about in the world. Even, I'm folding laundry, or I'm making breakfast, or I'm, whatever, driving a car. That can be framed as a game. And we can create a digital twin of that environment, which is NVIDIA has been huge in this recently because they realize just how important this is. Because especially for robots, getting iterations is important. You want lots and lots and lots of iterations so that it can learn things as quickly as possible. Well, if you have to do that in the physical world, then you're subject to physical constraints. So it's much better to do it in the digital world. And then you can crank up the time and have it go very, very fast, where you'll hear people say, oh, it has 10 years worth of learning. And it happened in a few days. And that's the idea, is that we have accelerated time in the simulation to have it learn to play soccer, or learn to fold proteins, or learn to drive a car, or whatever it might happen to be. And the more sophisticated the simulations are for that, the better we're going to have in terms of stuff that transfers to the real world and the real environment. And so obviously the world is not wholly digital, but at the same time, there is a level of fidelity beyond which it doesn't matter. And I'm reminded, and this is kind of interesting, for those of you who are in music, you might appreciate this. So I don't remember if it was Ray Charles or Stevie Wonder now. I'm blanking on it, but I think it was Ray Charles, who was involved in music production and was, very well attuned, like obviously ears very well attuned to music, and had long said that, okay, look, the 8-bit music, 16-bit, it's not good enough. It's still not as good as my studio equipment. Like I can hear the difference, he said. I can hear the difference between 16-bit audio and the analog tapes. And that continued to be the case until he hit 64-bit recording. And he said, okay, now you got it. At this point, it is actually as good. I can't tell the difference anymore. And that's significant because that is the level that we're trying to get to with these different simulations. We're trying to get the simulations to the point where the fidelity, it's not perfect. We know it's not perfect, but it's good enough to be able to train things so that they can then take that skill and use it in the real world. Now, this begs an important question. That is truly a kind of paradigmatic modern technology, in the sense that it is a modern technology insofar as it exemplifies the modern paradigm of approximation. I don't care how it works necessarily. I don't care if I've gotten the laws down. I don't care if I've, discovered the inviolable truths of nature. I just care if it works. Make it work. It's an engineering problem to make it work. And so I want to just, create a simulation that's good enough to train my robot so that it can fold my laundry. That's Wozniak's definition of AGI, artificial general intelligence. If you have a robot that can fold your laundry, if it can do, that kind of, and it's funny, but at the same time, it is actually amusingly sophisticated. But nevertheless, so we're headed very much in that direction. Okay, now let's talk a little bit about AI and complexity. So AI and complexity. One of the things that people ask, is AI just a stochastic parrot? Is it just a well-trained parrot, which is parroting back the patterns that it sees in its input data? So one of the ways of understanding what it is that neural networks do is that they are able to fit and reproduce arbitrarily complex phenomena depending upon how much data can actually be captured in the interactions and the weights, which is why you need different sizes of these neural networks to accomplish different things. That's what everybody is concerned about now with large language models. Make them bigger, scale. We want scale because they're getting better as they're getting bigger, even though the recipe for growing them hasn't changed. The recipe could be exactly the same. Now, obviously, people are trying to improve on this and make it better and faster. But the point is, just scaling it, just making it bigger is making it better. And it's making it better not just linearly in terms of it's getting bigger and faster, but it's also, we're starting to see emergent phenomena here where all of a sudden it can speak Persian. All of a sudden it can do, things that it wasn't able to previously do, as though certain ability levels have to be unlocked. And then they're suddenly unlocked, that anything that's smaller than that, like a brain that's smaller than that, can't quite do it. But once you reach a certain level of complexity, all of a sudden it can do it. Does this sound familiar? Right. And especially in the biological world, it's like, oh, okay, maybe there's an analogy here. Maybe there's something to this in terms of not just raw brain size, but brain complexity. And we should stop for a moment to say something about raw brain size, because oftentimes when people talk very prosaically about, the AI brain and the human brain, it's as if they're talking about the entire brain. And you realize that you share a good portion of the mass of your brain with a lot of other animals. So it's what's called just the brain, so the cortex, and the old brain in particular, so the reptilian brain. So the reptilian brain is called the reptilian brain because we share it with reptiles. And it's the sort of thing that, all right, well, if you're going to talk about like regulating your heartbeat and regulating your breathing and all kinds of other things. You've noticed, of course, that your dog sleeps and does a lot of the same stuff that you do and is able to control its muscles in a lot of the same ways. And it's also a vertebrate and it has, there are a lot of commonalities, right? And those physiological commonalities also extend to the structure of the brain. So the distinctly human structures of the brain, that's not most of the brain. So a lot of what we get with the neocortex especially, and the neocortex is that kind of wrinkly mess on the top of the brain. And if you stretched it out, then it would be about the size of a dinner napkin. And it would be about the thickness of, a few of them stacked together. And so the human brain has a number of layers to this. And you have cortical columns that run through there. And they're all, by the way, pretty similar. And you can tell something about, for instance, dolphin brains, very similar to this, but not as many layers, et cetera, and on down. But the point is, a lot of what we consider to be characteristically human happens in that dinner napkin and happens in the neocortex, the new brain. Neocortex literally just means new brain. And so it is this new brain that gives us a lot of the abilities that we consider to be distinctly human. And so part of what it is that we're going to be at pains to be after here is to try and understand what is different about AI. Well, what is different about AI and what is different about technology and the way that things are changing now is that we are starting to get to levels of performance that are distinctly non-animal. So we're starting to get machines that do things that the animals couldn't dream of doing. And so associative intelligence, being very insightful with, you can ask it questions about philosophy. I can't ask my dog questions about philosophy, and sometimes the whole dog, just bark, live in the present moment, give me bacon, that sort of thing. There's a value in that. But at the same time, so there's obviously something different going on. It's more like prefrontal cortex, neocortex style behavior. It's much more distinctly human behavior. And so anyway, that's what I'm after here. Now, the question is what AI is doing now significantly different than what humans are doing? And the key concept here, I think, is going to be in prediction. And I had somebody one of my good friends in AI, who came into my office a number of years ago. And I said, wow, you got to see what's going on in generative AI. It's crazy. What's happening now is nuts. And he was right. And this was in the GPT-1, GPT-2 days where we were just starting to scale these models up and see that, by the way, with scale, we get some almost magical things that are happening. And by the way, this is something I have to give a nod to Jeff Hinton here. So Jeff Hinton is one of the, so-called godfather of AI. He was a big machine learning proponent, and he was a machine learning proponent when it wasn't cool to be a machine learning proponent. He was somebody who was into this stuff and said, look, we need to scale. It needs to be bigger. It's going to work. It's capturing complexity and information in a useful way that is interesting and will be very interesting, but you've got to scale it. It's got to be a lot bigger. That long ago, it was hard to see that he was right. But by the time we get Google around the 2010 era doing image classification with pictures of cats. So they went about trying to create, is this a picture of a cat sort of classifier? And as it turns out, that's a really hard problem because sometimes you see, the whole cat. Sometimes you only see part of the cat. Sometimes it's facing you. Sometimes it's not. Smaller, bigger, different sizes, shapes, colors, and otherwise. There's a lot of variety. And there's no one thing necessarily that it has in common. And so it's very difficult to do that kind of classification task. And so they fed it 10 million pictures of cats because the internet in 2010, there were actually 10 million pictures of cats. And now there are a lot more, but nevertheless. So that worked. And that worked. Hinton was vindicated. And this kind of kicked things off. And it was like, oh, yeah, there is something really interesting here. What else can we do with this? How far does this go? And so anyway. Now we're getting to where prediction models, so generative AI. And generative AI comes in at least a couple of different flavors that are worth discussing. So the transformer-based architecture with respect especially to text prediction, where you have a, embeddings layer of vocabulary. So it's, gotten used to, okay, how all these concepts relate to one another. It pays attention to different words in the sentence and can keep a bunch of things in mind to then predict what is the next word. Or now, what is, as of June 2024, following a research paper from the previous month or the month before that from Meta, doing multi-token prediction, where it's not just predicting one, but it's predicting several things at the same time, potentially being able to think about an entire sentence at once, which is kind of what we do. Or maybe an entire paragraph, an entire thought, whatever a thought is, like however much in advance one can prepare to talk about things. Again, this is worth stopping to think about for a second, So how far in advance do you actually think? When you're talking to someone, even if you're doing like I am right now and giving a lecture, I still have some notes, right? To make sure that I don't forget anything. So it's different topic headings in trying to figure out, okay, what did I want to say next? What is the next topic? Oh, that reminds me. And that leads me into this new room of the memory mansion sort of thing. And then I can remember all the different stuff that I wanted to say. Well, how far in advance does that go? When you're talking with a friend at a restaurant, how many words, how many thoughts or sentences in advance are you actually thinking? It might be more than one, but it's probably not more than 3 or 4. You might have a sophisticated idea that it's going to take you a little bit to try and get that out. But at the same time, the information is limited. Like, how much do you actually want to convey at any given time? It's not an encyclopedia's worth of information. It's probably not more than a few sentences. So it's going to be very interesting to see what happens when it is possible to have predictive AI that is actually working in those same quantities and maybe even much bigger. So anyway, that's very interesting. But what's really salient here is the question of what prediction is and the role of prediction, especially in biological intelligence. And so for humans in particular, biological intelligence in the animal kingdom and then also with humans, one of the principal capabilities that we get with a bigger brain, and a bigger brain had better be worth it because it's really expensive. It takes something like 30% of our energy. So it's a really expensive organ when we're using it, which is why we try most of the time not to use it. But I'm not kidding about that. So this system 1, system 2, like the habit thing makes a lot of sense in terms of the economy of energy. And this is a brain that is, what is this, like 10 or 20 watts, something? It's not very large, right? So the brain is not using a tremendous amount of energy, especially compared to, your average video card in a computer, which is using 10 or 20 times that or more. And then nothing compared to the massive servers that are now trying to serve intelligence. We're orders of magnitude less efficient than the human brain at present. But that's always the case with technology, right? You get started at first and it's just gratuitously inefficient. And then hopefully later it becomes more efficient. That's what's happening with nuclear fusion right now. So anyway, but prediction. So there is some thought that prediction is one of the principal things that we get with a larger brain and with a more capable brain, such that prediction is very valuable. Now, this is something that if you've spent much time either in contact with the military or in playing war games or any kind of strategy-based game, the most valuable thing that you can have is any kind of real detailed prediction about what your opponent's likely to do. If you know what they're doing and you know where they're going to be, massive advantage. So intelligence is a big deal. And in this case, intelligence, I'm talking about like spying and espionage and that kind of stuff, right? Like, gathering intelligence. So getting information. So getting information is just crucially important. And that's the sort of thing. This is why you hear like with computers in World War II, with Turing and all the others involved in, okay, let's decode the Nazi algorithm to actually send encrypted communications. And that was a big deal when they were able to really decode those messages. Arguably that, really turned the tide there. And so information is crucially important. And that information can be thought of in terms of prediction. And so one of the human brain's greatest capabilities, and animal brains to some extent too, but we're even better at it, is in prediction. And so strategy games. If you've ever played a strategy game against an animal, so to speak, now you're fighting a pack of wolves or something, things are not going to go well for you probably. But at the same time, we tend to do better with strategy. We tend to do better with strategy games and that kind of predictive based intelligence than animals do. And that outfoxing an opponent at something is tremendously important in terms of, being able to survive. And so that kind of thing, it makes sense that it characterizes human intelligence. It makes sense that it characterizes biological intelligence. And even more so then, okay, so let's dig into it. And what is it? So what is that predictive capacity? What does it consist of? Well, if I want to know what someone's going to do next, it's not just like predicting the lottery numbers, right? It's not just like, oh, here's a string of numbers. This is what's going on. It may eventually distill into a single location. Where is that army going to be tomorrow? How are they going to attack? And I know that they're going to attack here. That may be a single piece of information, but that single piece of information likely is a product of understanding, having a model of mind so that you can understand how the other person is thinking. Now that turns out to be tremendously valuable. It's also really hard. And so it makes sense that it would be a higher order cognitive capacity. And it is, by the way, the kind of things that we're now seeing with large language models is that they're very good at certain kinds of model of mind questions. My favorite example of this is the one that came up very early with ChatGPT, where they were trying to figure out if it could keep up with stories and logic and questions and things of this kind. And so a very simple model of mind question is, you've got these guys with boxes. And so there's a cat sitting on the table and there's a box sitting on the table. And so you say, okay, well, John puts the cat in the box and then John leaves the room. And then Steve takes the cat out of the box and the cat leaves and goes scampering off. Then John comes back into the room. Where does John believe the cat is? Well, a human is going to tell you, John believes that the cat's still in the box because, that's where he put him. And so he believes that, and that would be the right answer, which is not the same as using all the information because John didn't have all the information. And we know based upon his limited vision that he didn't have all of that information because he was out of the room. Where does Steve believe that the cat is? Well, Steve believed the cat left the room. He's gone. So those two, to be able to tell the difference between those two requires a certain amount of perception, a certain amount of model of mind. And what was amusing is that ChatGPT actually answered and said correctly for the two different figures, and then also answered from the perspective of the cat, that the cat knew where it was as well, it's just funny, it's because it wasn't asked that, but it ended up answering the question anyway. And so anyway, and something happened recently with Claude, and this is, I believe, with Claude Opus. So this would have been like spring 2024, where Claude was asked, a series of questions, and they were trying to do needle in a haystack test. Well, needle in a haystack test is where you give it like an entire book, War and Peace. And then somewhere in the middle of War and Peace, you insert like a pepperoni pizza recipe. And the idea is, can you, in ingesting this massive quantity of information, huge context window, can you pick out the pepperoni pizza recipe? And Claude was not only able to pick out the pepperoni pizza recipe, but responded and said, hey, by the way, I think you're trying to trick me because that doesn't resemble the remainder of the text in the book. That's interesting. How much should we make of that? Nobody knows. Nobody really knows why that happens. That it seemed to have a kind of awareness of that is very interesting. And so that's the sort of stuff that's happening now, where we're making these discoveries that, by the way, the models can do this, and nobody really understands why, and nobody really understands what's going on, just like the human brain. So that's what happens with grown intelligences. Now, the real question that arises at this point is with respect to formal logic, because everybody's very interested in being able to use these systems for obvious reasons to have it do things that humans do. It just so happens that the jobs that humans do now are largely not based upon this kind of human level associative intelligence. I mean, unfortunately, right? Like being able to do a factory job or being able to do accounting or being able to do a lot of other things are rules based. They're discrete. They require much less than the full brain to be able to do them. But at the same time, these systems are struggling to be able to get the formal logic right. And the question is, how? How is it that humans are able to do this? How are we able to do mathematics? Taking someone like Hans Bethe seriously, perhaps. Hans Bethe was a mathematician in the 20th century, and he wrote a little book and had a comment in there, which I absolutely adore. And he says at some point that, there almost has to be something wrong with you to be good at mathematics, which is funny because it's as if to say it's not really natural. It doesn't seem like it's really natural, and it doesn't fit with a lot of our natural intelligence and our capabilities to be able to work with formal systems in this way and to be able to work with mathematical theorems and do this stuff that is so abstracted from the real world and is so abstract just in general. And so that's funny. And like I said, I'm a math person, so I feel a little bit more comfortable relaying that, but nevertheless, and identifying with it maybe. But so anyway, that's funny. But the real question with formal systems, and the key with formal systems that I want to point out, is something that we're going to encounter. And I want you to keep this in mind as we're going through. And we're going to hit this almost at the very end with Andy Clark. And Andy Clark is a philosopher who wrote with David Chalmers the Extended Mind article that happens right before the end for us. And Andy has, in one of his books, he articulates the concept of scaffolding. And scaffolding is really important. And I'm going to argue that it's really important, especially for formal logic systems and for habit-based, like, again, with Kahneman System 1, System 2 thinking systems. So it's really important there because it allows us to build on a firm foundation and to increase expertise in terms of like piano playing. Can I play, Chopin's Fantasy Impromptu? No. But could I get there? Well, okay. That's going to require starting from wherever I am and then starting to build these little bits of habit, these little bits of capability, so that I have to think about them while I'm building them. But once I've got it, then that gets pushed into habit. Again, System 1, System 2 kind of thing. Gets pushed into habit. I don't have to think about it anymore. And then I can come back and work on the next little bit up, and I just build incrementally. Well, that incremental building is what Andy referred to as scaffolding. Now, what he was talking about wasn't piano playing. He was talking about concept creation. And so concept creation is the sort of thing where we tend to build concepts and ideas that scaffold upon one another. So those concepts build upon one another. So I get a base level understanding of something in mathematics, maybe algebra, maybe, just adding and subtracting, multiplying and dividing, right? Think about our mathematics education. So you start with like third grade and you're building up these sorts of, base level facts, how it is that you deal with equations and deal with basic operations, and then add algebra, then add, trig and geometry and calculus and linear algebra and differential equations and so on. And so you build up incrementally. Well, that building up is, again, a kind of scaffolding. Now, where this becomes eminently practical is in the domain of modular programming. And so modular programming, so object-oriented programming, building these little modular atomic bits. The idea there is that you build modules and you have the modules robust enough and polished enough such that I don't have to understand how it works. So once I know that it works, I don't have to think about it anymore. All I have to understand is what goes in and what comes out. As long as I understand what goes in and what comes out, I'm good. I can use that module. And so I can do JPEG decompression. I can do, MP4 decompression. I don't have to understand how that algorithm works. It doesn't matter. All I have to do is call the right module. I understand what the input stream is. I understand what the output stream is, and then I can use it. And that's the sort of thing that works extremely well in programming. And here is the key. It allows for a singularity of complexity. The singularity is such that the scaffolding does not have a ceiling. There is no limit in terms of the complexity that you can build with these systems just by building module upon module upon module, which is why we end up with, if you showed someone a modern day operating system that was living back in the, 1950s or 60s, it would have looked like utter magic. And this is something that is, tons of these little modules built upon each other, each of them working very consistently and independently. And that's the key, is that it's working very consistently. This is what the large language models can't do right now. This is why they can't quite get there in terms of being able to, if you put a prompt in that says, write a new version of Photoshop, it's not going to work. It's not going to be able to do it. It can try and decompose the task and break it into 1,000 different pieces or more, probably a lot more for that. Break it into a lot of pieces and then build up each of those pieces individually. The problem is it's not able to iterate and eventually get all the foundation layer stuff right and then slowly scaffold and build on that. It can't do the scaffolding process because it can't get the foundation stuff right consistently. But what happens when it does? That's the question. What happens when we do get to the point where they're able to program consistently? They're able to create these atomic concepts and things that you can build upon and can scaffold upon, and especially things that you can scaffold upon in an online learning capacity. In other words, right now the models are frozen. The models are frozen, which means that they finish training, and then when you use them at inference time, when you actually talk with ChatGPT, it's not getting smarter. It's not learning from what's going on. It only uses that context window to try and change things. And there are other tricks, but the model itself stays the same. The brain doesn't, right? Every time you interact with the brain, it changes. Well, it's really hard to balance that kind of system. It's really hard to get this right, but it's not impossible. And there are a lot of people working on that problem now. And so when it is possible to get, these foundation layers, when it's possible to enable scaffolding by getting those things right, and then to have it learn actively, these are just engineering problems at this point. At a certain point, it's going to cross a threshold where it is possible to give it the prompt, create Adobe Photoshop, and it'll be able to do it. What happens then? That, I think, is going to be very interesting, because that's the kind of thing where, off to the races. Like I said, and there's a reason that I use the word singularity. Now, I'm not using it in the sense of the singularity, not Venge's singularity, where he's talking about a singularity of intelligence. And this with artificial superintelligence, which is this kind of intelligence explosion. That's not what I'm talking about. That is salient. That's certainly something that's relevant to what we're talking about here. But I'm talking about a singularity in terms of complexity. There's some thought, and people don't consider this very often. It doesn't get talked about very often. There's some thought that human intelligence itself represents a kind of singularity. That the human ability to scaffold concept upon concept, this can happen without limit. And so a pianist does not cease to get better because of a mental problem. It's not a scaffolding problem. It's that they've reached a kind of physical limit for what you can do with the body. And so that's very interesting. And that should give us reason for thinking that these sorts of intelligences, if we can create something, if we can grow something that thinks like we do in this way and is able to successfully scaffold from simple concepts to more complex skills and abilities, we're off to the races. Now, the question for us, of course, is how do we think with that sort of thing? How do we interact with it? And what in the world is going to happen to human society at that time? So we'll get to that. And that's why I want to begin with Sam Altman's article and then kick off our exploration from there. So I hope that you found this interesting. I hope you enjoy the content.